All right. So presenting, what's the point of geometry? What's the point of what we're doing here? This is Mr. Bechtel's joke. There's no point. Quit school, join a clown college. That's not true. We're just kidding. The point of geometry is to work through the idea of taking that which you know and the rules that you have learned, putting them together to create and prove rules that help further our understanding. So geometry is heavily focused on this idea here, proof. So to take the definitions that we talked about yesterday, or at least the undefined terms, and then those few definitions of segments and arrays and such, along with a couple things we're going to talk about next called postulates, and try to prove further further mathematical ideas to hurt your cells. That's maybe brain cells. But to prove anything, we need some rules. So what we're going to start with is what are called the postulates, the 5 postulates of geometry. So geometry, the formal geometry was created by Euclid, or the Euclideans in ancient Greece. Actually, he lived in, I believe, Alexandria, Egypt, but he was part of the Greek civilization, and he kind of came up with the formal mathematics that we kind of study today in school. And he had some slightly different postulates than we're going to go over. A postulate, also called an axiom, is something that is accepted to be true without proof. That doesn't mean it's not true and we're just going to accept it. It means that these are kind of intuitive ideas based around our building block objects, those undefined terms, points, lines, and planes that are intuitively true, things that we can kind of draw out and visually see and understand without the need for proof. And if we accept these 5 things, we can kind of build and prove all kinds of other mathematical relationships that are much more complicated than these things, as long as we sort of accept these as our building block, our basis of things. So, oops. So a postulate is something that we just accept to be true, sort of like when your parents say, because I told you so. If your parents say that, I know mine did. All right, so here are the first 5 postulates that we're going to have in our course. So the first one, it says, through any 2 points, there is exactly 1 line. Again, fairly intuitive. If you have 2 points, there's only 1 line that you can draw that goes through those 2 points. The second one, through any 3 non-collinear points, there's exactly 1 plane containing them. A little bit more complicated, but it says if you have 3 points that are non-collinear, meaning they're not in a straight line, there's going to be a plane that contains all 3 of those points. Now the plane might not be drawn or shown, but there is a plane that would have all 3 of those points if we sort of drew it out. This is sort of similar to the reasons I mentioned briefly yesterday that 3-legged stools are extremely stable, because if those 3 legs, the ends of those legs can be points, and no matter the lengths of them, if one is shorter than the other or one of them's long, they're just not even, the stool will always still sit flat. It'll never have any wobble to it, because those 3 points that are at the end of the legs that come into contact with the ground, which is a plane, will always be coplanar, no matter what. But if you add a 4th leg to a stool or a table or something, that's when you sort of get the wobble, because it's possible that 4 points would not be coplanar. A little less intuitive on that second one, but still something that makes sense. The third one says that if 2 points lie in a plane, then the line containing those 2 points lies in the plane as well. So this makes sense to me when I think about a plane as a piece of paper. If I have a piece of paper and I draw 2 points on that plane, and I draw a line that goes through those 2 points, there's no way for me to draw that line in a way that isn't on the paper as well, that isn't on the plane as well. So again, another intuitive idea, but something that's useful for us to build more complicated ideas from. The fourth postulate says if two lines intersect, then they intersect in exactly one place. Again, it would be very difficult to draw some lines that cross twice or three times, right? At least in terms of what we think about as lines. There are other types of geometries that define a line differently. Some geometries define lines as circles on a sphere. It's called spherical geometry. If you define a line to be that, well, it kind of messes things up. But our lines are straight paths with no thickness. They continue forever. They only are going to cross at one point. There's no way to draw straight lines that intersect more than once. And then the fifth one, the last one for us, is if two planes intersect, then they intersect in exactly one line. This one's a little harder to visualize, but I like to think about the walls of a room. So if you have two walls and they meet in a corner, that corner is where those two walls intersect each other. And those walls can be planes. Well, then the corner of the room is a line. So where those two walls intersect, they form a line. So these are the 5 postulates. These are what we're going to take, along with a few other ideas, to build more complicated mathematical relationships. And if you start with a different set of postulates and a different set of undefined terms, that's where you get things that are called non-Euclidean geometries. Euclidean geometry is named after Euclid, the guy I mentioned earlier, who created this system of geometry, which is kind of most like our world around us. There are other types of geometries like geometry on a sphere, because contrary to popular belief, the Earth is a sphere, and if you're wanting to figure out how things work, you know, think about the way a plane flies around the Earth. A plane can't actually follow a straight line because the Earth is not flat. Again, it's a sphere. It has to follow a circular path around that sphere. And circles on spheres behave very differently than lines on flat surfaces. And you have to take that into account. So that's a different type of geometry that's actually very useful in plane navigation, among other things. All right, but we're going to stick to Euclidean geometry, straight lines, points, flat plane, that sort of stuff. All right, a couple questions to think about. I'll just get them up here. Any 2 points that exist in the universe are always collinear. So if you have 2 points, there's always a line that will pass through those. So it's not useful to say that just 2 points are collinear, because that's true of all 2-point pairs, right? There's always a line that would go through both of those. For collinear, it's really more important if we have 3 or more points, because then 3 points aren't always all in a straight line. Which postulate explains the fact that 2 straight roads cannot cross each other more than once? So one of our postulates said, you know, when 2 lines cross, they only do it in one place. Using the definition of a plane, what are all the things that can be used to show that a plane exists? Well, a lot of different things. If you have 3 points, they make a plane. If you have a line and a point, those could make a plane. 2 lines can make a plane. All kinds of things that could create a plane for us. And then this is the thing that I was mentioning here. Why does a 3-legged stool never wobble? Well, that's because 3 points are always going to be coplanar. So they'll always sit on the flat surface of the floor, whereas a 4th point, once you add a 4th point in there, it's possible that 4th one is not in the same plane and will cause the stool to not sit flat on all 4 legs. All right, so from here, the homework that was assigned was this for 1.1. A lot of questions were asked about this from 4th hour, so I just want to make sure to go through this. The pages 9 through 11, you can find that either if you went to go get your textbook at UHS already and you have that, you can just go to these pages and do the problems. I also uploaded a PDF of chapter 1 into our Google Classroom. You'll find that under the classwork tab, there's a textbook resources section, and you can click on that and find it there. A lot of these problems kind of tell you what they're about. Straight up practice, more thinking problems, and then some challenging ones at the end. I'm not going to look over all your homework. You're not going to scan it in or take a picture and show me every single problem you do. That doesn't mean don't do them. It's actually very important that you do them, because when we do quizzes and things, I could pull questions from your homework from any part of it. But the one that I am going to ask you to make sure you do really thoroughly and put a picture, attach a picture of it to Google Classroom, is this one. So number 38. So for 1.1, problem number 38, there is an assignment in your Google Classroom. So if I go there on the classwork tab for week 2, I have all these different things in here. For week 2, I'm actually going to drag this one down. Homework 1.1, if you click here and view the assignment, you can see some people already turned it in. But if you do that problem, you can attach, there's a place for you to actually attach a picture. So do that however you feel most comfortable. Some people take a picture of it on their phone, then email it to themselves, and then attach it from there. Some people do that, but then they put it in a Google Doc, however you want to put that on there, and then attach that to the assignment, okay? I'm not going to mandate that you do it one way or the other. Just make sure that that's that particular problem. So number 38 for this assignment gets attached on there. And that's the one that I'm going to look at and give you feedback on and a grade for the homework assignment based on this problem. Again, it won't cover everything. There are other things in that homework that is not covered on problem number 38. So make sure you do the other problems as well. Any homework questions in the chat, or feel free to speak out if you want to.
I looked ahead at 1.2 and it confused my soul.
Sure. So 1.2, we're going to start that right now.
Okay.
We're going to see how far we get, and let's see what you have questions with after that, okay? Again,
Okay.
I don't know exactly how far we're going to get, and we might need to, you know, go back over this on tomorrow or slow things down for next week. We'll see. All right, 1.2. So this is 1.2. We're going to be starting the next section. We're going to further use those terms and postulates and things that we just learned about, but we're going to talk specifically a lot about segments here. So we have another postulate. I'm going to bring all this stuff up here. So this is called the ruler postulate. It seems kind of silly. Basically, the idea of the ruler postulate is we can do two things. We can measure the length of a segment using a ruler or some other measurement device. But another thing we can do is we can actually, on a segment or on a line, we can overlay what's called a number line. So we could think about these units here as being a number line, and then the points that we put on it, we could call those numbers the coordinates of those particular points. And that allows us to use like arithmetic and stuff to actually figure out lengths of segments that are on a number line. And we'll see that here. So this is, again, a postulate. It's something we sort of just have to accept to be true, but kind of makes sense that we can measure a segment. That's an intuitive idea. All right. So distance or length, that's a really important concept for segments. We're going to need to know the length of segments or the distance between 2 points, which is sort of the same thing. We have a few points here, and we've overlaid a number line. And each of these points is given a coordinate, the number that's associated with it on the number line. We can find the length of these segments by a process of, my fault, let me do this. Taking the absolute value of the difference between two coordinates. But why do we have to use absolute value? Well, let's look at it. Let's think about if we just do that process without absolute value. So let's say we wanted to know how long the segment EC was, from E to C. Well, let's say we just find their difference. Let's take their coordinates and subtract them. So if I do E, the coordinate for that is -2, or sorry, -4. And then C, the coordinate for that is going to be 2. So the difference of their coordinates, that just means I subtract them. And when I do that subtraction, I get -6. So the length of EC is -6. What's the problem with that? Why does it tell me that I actually need to do the absolute value?
Because you can't find, like, you can't negative measure something. Like, you have to find the exact space between it, you know? Like, it has to be positive.
Absolutely. So that is totally what I'm looking for. And I see a couple people sent messages to me saying distance can't be negative. Yeah, so whenever we're talking about distance, we don't ever say that it's negative. So if you were to drive to Danville, which is about 30 miles away approximately, you wouldn't say, oh, that's to the east, which is positive, so that distance is 30 miles. But if we're going to Bloomington, that's west, so that's like -40 miles. You don't assign distance a negative value because of direction. Now, when we care about direction, occasionally we care about negatives and positives, but when we're just talking about distance or length, you're right, we never use negatives. We just want to know how far apart, how many units is this distance. And the way we can always assure, or one way we can always assure a positive is just to take the absolute value. So we just add absolute value in there. And that gives us a +6, so that these are 6 units apart from one another. There are other ways we can assure a positive distance, and like the distance formula has a different way of assuring positive distance. It involves squaring or raising the second power. You'll never end up with a negative when you do that. So again, let's just do one more example here really quick. Let's find the distance from F to D. So go ahead and do that. Find the distance from F to D. So I'm showing my calculation here. I have the coordinate for F minus the coordinate for D. And again, because I have the absolute value bars here, I don't actually care. Yeah, so I'm seeing the right answer in the chat a couple times. I subtract those and I end up with -5.5. But again, since we're doing absolute value, we just get 5.5. So the length of that segment is 5.5 from F to D. We could also count it since there's a number line here, right? We literally just count the units. 1, 2, 3, 4, 5.5, 5.5. But we won't always have, you know, a number line overlaid that we can just do that and count it. All right, I'm gonna stop writing. Okay, so here's a really important idea that's first getting introduced in math. In geometry specifically, we have this idea of congruent. Congruent is very important. In this example, it's going to seem very over specific, maybe is a way to say it. Congruent means two things. It means that they are the same shape and that they have the same measurement. So for segments, that's really easy. Two segments are obviously the same shape. They are both segments. And the only measurement that is associated with a segment is the length, right? So if we have two segments that are the same length, we say that they're congruent to each other. This gets a lot more complicated when we're talking about more complicated shapes like triangles or other things, because triangles have, well, they're triangles, but they have lots of measurements, right? And so in order for those triangles to be congruent, all of their measurements have to be identical. They have to be the same. So congruent is a little stronger than just saying something is equal. This is the symbol that we have here. It's the congruent symbol. We'll use it all the time. It's an equal sign with this little squiggly on top of it. It's technically this symbol means the same shape. It's the similarity symbol, so it's equal in number, equal in measurement, and similar, it's the same shape. So it's really kind of two symbols put together. But for us, it's going to be one of the most common ones we use throughout the year, the congruence symbol. So we have these two statements up here, and they pretty much look the same. And for our purposes right now, again, since we're dealing with segments, they're pretty simple objects. They pretty much mean the same thing, but they don't in a really specific technical math way. This means that this segment PQ is congruent to this segment RS. So this tells me that I have two segments and they're the same exact length. This means a similar thing. This means the distance from P to Q is equal to the distance from R to S. There might be segments drawn here, there might not be. It conveys a little less information, but it also sort of just means the same thing. They're very interchangeable. I am not going to be super picky about it, but it is nice for us to understand that one is specifically talking about the geometric objects themselves being the same and the same size. And the other one is meaning that these numbers that represent their lengths are the same. It's a small difference, but it is a difference, and it's nice to know that. So again, this means congruent or congruence. It means these two things are congruent to each other. They're both segments and they have the same length. This means they're equal, equality. It just means that their lengths are equal. Now, another little thing here, this is the way on geometric drawings that we actually mark congruence. So if we want to show that this segment here is congruent to this segment, we use these little tick marks. So you're going to see them on geometric drawings all the time. So everything that has a single tick mark is congruent to everything else that has a single tick mark. So there might be 3 segments in a drawing that are all equal length to each other. They could all have this single tick marking. Maybe we don't know the length, but we do know that they're equal. If there is another set of congruent segments, we have to use more marks. So for instance, if I added in here some more, if I had some more things drawn in here, like I had another segment that was like this. And I wanted to show that these two were equal to each other, but they're different from these. I would just use 2 markings on them. So now I can see that ones that have a single tick mark are equal, they're congruent to each other. And the ones that have 2 marks are equal to each other, but they're different from these. And then if I even had another set of them, another set of segments, and I wanted to show that these were equal but different from the others, well, I'd have to use 3, which I hadn't drawn this so small. And you can see that the more sets of congruent things we have, the more markings we have to use. In general, we won't really go above this. 3 is pretty much the most we'll need. Though obviously we could make a drawing with as many sets of congruent segments as we wanted to. So it could get out of hand, but I don't think that it will. Okay. So we'll learn a lot of different little markings that our pictures can have to indicate information to us, like congruence and things like that. But this is the first one. Tick marks mean congruent. Yeah, again, equality simply refers to the numbers that are represented here, their lengths, whereas congruent refers to the shapes being the same. It's a small difference, but it is an important one. All right. I made mention of this idea yesterday, betweenness. A couple of the words, a couple of the definitions that we had use this word between. Technically, between carries a lot of information about it. So when we say something like B is between A and C, the word between is really conveying more than just it's in between them. There's a little more mathematics to it. So it means these 2 things. It means that all 3 points have to be collinear. So our point B has to be on the line between A and C. It can't be like up here or up here and kind of in between them in terms of, if we just use that word in English, it's not very precise, right? It just means that the area that's in the middle of them, the point is somewhere in there. But technically in geometry, between is much more specific than that. It means that it's literally on the line in between them. And then the other thing that it means is there's a mathematical relationship between all the segments that we have. If you take the length of AB plus the length of BC, that has to equal the whole length from A to C. This is actually a postulate, but it makes sense, right? If we split a larger segment up, well, then the sum of those two small pieces have to be equal to the big one. That is an important idea. But again, notice here in this equation, AB does not have the line over the top of it, because the line over the top of it refers to the segment, not the length of the segment. So what we're saying is here, the length of AB plus the length of BC is equal to the length of AC. If we say the segments add together to make the big one, that's not technically correct, because you can't really actually add segments together in that same way, the same way we can add numbers together. So I was alluding to this, but the last statement there is actually what's called the segment addition postulate. So if some point is in between two others, then we know there's this mathematical relationship between the segments that we have. The two pieces have to add up to equal the bigger one. And what that allows us to do is, if we have some numbers or expressions there, we can actually solve some math equations like this. So here we go. I'll take this information down here at the bottom and kind of write on my picture. So we're going to ask the question like this. So if AB is equal to 2x plus 7, so I'm just kind of marking that this segment is 2x plus 7, and BC is 28, and AC, so the whole thing, I'm going to mark this way, the whole thing is equal to 4x. So this is me kind of labeling a picture with the given information. We're going to see a lot of these throughout this particular section. This relationship right here lets me actually set up an equation. Well, I can say that 2x plus 7, which is the AB part, plus 28, which is the other piece, well, that needs to equal the whole thing, and that's guaranteed by this segment addition postulate, which is something we accept to be true, but also intuitively, it kind of makes sense that it's true. And then we can solve for x, and then if we wanted to, we could use that to figure out any of these segment lengths that are on here. So I'm going to go ahead and do that. I'm going to combine like terms first. And then I'm going to get all of my x's on one side, so I'll subtract 2x. We're sneaking in algebra here on you guys. And then I would divide by 2, right? And 35 divided by 2 is 17 and a half, 17.5. Now, that's the value of x, which is cool. That's something that we could do. We could ask what the value of x is, but we could also use that to figure out all of these segment lengths here. So if we wanted to figure out the whole length of AC, we could go ahead and substitute that number that we just found in here. We could do, all right, well, this thing's going to be 4 times 17.5, which is 70. So we can figure out that AC is equal to 70 units, whatever that would happen to be. And then similarly, right up here, we could figure out that AB is 2 times 17.5 plus 7. So that's 35 plus 7, so this would be 42. So we found all of the specific lengths of the segments that would kind of solve or satisfy this situation here. And you could even, once you have all the numbers, you could even just double check it. because this one is supposed to be 42. This one's supposed to be 28, and this is 70. And this one certainly looks in my picture a lot smaller than this one, right? 40. This is an important thing that I need to mention here is when we make a picture, we might not know the specific lengths going into it. So we might draw it in such a way that one of the lengths is much shorter than it's supposed to be and one of them is much bigger or something like that. But the picture is just to illustrate the sort of betweenness. We don't know the specific lengths of them going in, so we have to kind of, you know, use our imagination that, well, really B should be kind of more over here to make this picture accurate. But the picture was just an aid in terms of helping us solve the problem. All right. I want to go ahead and stop right there because I don't want to rush through this. So obviously we didn't get through everything. We're going to pick up where we left off here today. We'll pick up tomorrow. Again, I'll make some adjustments to things, but make sure you're doing the homeworks. Try the 1.1 homework. And if you're totally done with that and you feel like you can kind of pick this stuff up on your own, you can go ahead and start the 1.2 homework. Again, we're going to meet again tomorrow, try to finish up as much of this as we can. And I will have an office hours on Wednesday afternoon and Friday afternoon for people that are having questions. So try to get these assignments done or do as much of them as you can, and I'll see you guys tomorrow.